In this video, we're going to quite literally just do one example. We're going to do one problem. And it's kind of the sort of crescendo of everything we've been doing in chapter 3. All we're going to do today is find all of the real zeros of a polynomial using the rational zero theorem. What the rational zero theorem is going to do is it's going to help us kind of create sort of a menu of guesses for possible first zeros. And then from there, we're going to use everything we did in 3.4, which is using synthetic division to find a zero and start breaking the polynomial down slowly. So first, we're going to talk about the rational roots theorem. The idea is if I have this polynomial with integer coefficients, if I do have a rational zero, it's going to be somewhere at plus or minus p over q, where p is a factor of the constant term, that's this guy, and q is a factor of the leading coefficient, which would be this guy. This doesn't make a whole lot of sense when you look at it just as it's written. So let's instead kind of wrap our heads around a particular example. So let's suppose I wanted to find all of the possible zeros of this polynomial. We're not even just talking about rational, just all the possible zeros. I'm going to have to start with rational zeros, just based on the fact that I have a rational roots theorem. I don't have an irrational roots theorem or a real roots theorem because there isn't really one. So here's what I've gotten. R is going to be the collection of all of the possible things I could check. So first, we're going to look at the constant, which is going to be my numerator. So what I'm going to end up doing is it's always going to be plus or minus the factors of my constant term, which is 3. If you notice, I don't pay any mind to the sign because that's already paid attention to there. So let me go ahead and erase that now so that that's clear. All right, now I'm going to take a look at all of the possible factors of 2. This is going to be a really easy one because I've got a prime constant and a prime leading coefficient. But let's talk about all the different factors of 3. So all the different factors of 3, there's only 1 and 3. Those are all of the factors there are of 3. Now let's talk about the factors of 2. All of the factors there are 1 and 2. So now, what does this even mean? What we're looking at here. Let's talk about all of our possible factors. So, or all of our possible real zeros. So we'll start with these guys, 1 over 1. So we've got plus or minus 1 over 1 is 1, boom. So we got to check plus or minus 1. Next, we'll do 3 over 1. So 3 divided by 1 is 3. So I've got plus or minus 3. Now, I'm going to take a look at the factor in the denominator. So now I've got, boom, plus or minus 1 over 2. And plus or minus 3 over 2. So what we're going to do is we're going to check 1, negative 1, 3, negative 3, 1/2, negative 1/2, and 3/2, negative 3/2. If there is a rational zero in this thing, it's going to be one of these things. So it's going to be a lot of guessing and checking. And we're going to be guessing and checking until we find one that when we use synthetic division on it, we get 0 as a remainder. Whew. Okay, so we already talked about these. So R2 and R3, we set up our rational zero test, and we found already from the previous slide that R was plus or minus 1, plus or minus 3, plus or minus 1/2, or plus or minus 3/2. So what I'm going to need to do is just start going. Just start guessing and checking. So I'm going to start with plus 3. So we do our synthetic division. We've got 2, 4, negative 1, negative 6, negative 3. All right, the table's set. So let's start with 3. Why not? We'll start with 3. So we drag the 2 down, we get 6, 10, 30, 29, then we get 97, 91, 273. Okay, so 270 is my remainder. No, what I really need here is I need a 0. 270 is super not 0. So, okay, we tried 3, doesn't work. So if I even thought of this as like, listing out all of my possibilities, I've got 1, -1, 3, -3, 1/2, -1/2, 3/2, and -3/2. I know that 3 is not going to work. All right, so now let's go ahead and try -3. All right, so now we've got 2. 2 times -3 is -6. So then I get -2, 6, 5, -15, -21, and then 63, 60. No, so -3 doesn't work. All right, it doesn't feel like we're making a whole lot of headway here. But we know what we're checking, and this is really just a matter of time and just a matter of patience. So let's try 1 now. And yes, I already know what it's going to be, but let's just go ahead and try 1. So we try 1. So we take 2, drag it down. 2 times 1 is 2, 6, 6, 5, and then 5, -1, -1, -4. All right, so it's definitely not going to be 1. So ultimately, all we're doing here is we're looking for a remainder of 0. And when we have a remainder of 0, we're in great shape. All right, so now let's go ahead and try -1. All right, so we drag the 2 down, -2, 2, -2, -3, 3, -3, 3, 0. Oh my gosh, that's it. We've got 1. That's tremendous. So here's what we've got. From here, I know that since -1 is a root, x plus 1 is a factor. And now from here, I've got the remaining polynomial. This was to the 4th, so now this is 2x cubed plus 2x squared minus 3x minus 3. All right, we're doing it. We've done it. We're getting there. So now, here's what I'm going to do. I'm going to look at this thing and I say to myself, like, oh man, I think that factoring by grouping is going to be really, really nice here. So let's just go ahead and do that. I've got what I need from the rational zero theorem. If I found that I still couldn't break this down more, I would use all of those things I had before and try breaking down my new polynomial. But for right now, I already know that I've got x plus 1 as a factor. And so now I'm just going to go ahead and break down this 2x cubed plus 2x squared minus 3x minus 3. And so let's try factoring. So if I use grouping here, I'm going to go ahead and take a 2x squared out here. I get x plus 1. I'm going to take a -3 out of here. I get x plus 1. And so now I have x plus 1, 2x squared minus 3. And then don't forget I still had my x plus 1 up there. All right, now 2x minus 3. This is huge. I'm like right there. I can use quadratic formula from here. And if you don't mind, I'm going to go ahead and do that over here. Let me clear all of this out. Like I said, we're only doing one example, but this is a really good example. So now, 2x squared minus 3. So right out of the gate, I see that I've got one of my horizontal intercepts. I see that I've got a double root here at -1, but that's fine. I've got -1, 0. Now let's take a look at this thing. A is going to be 2. B, since I don't have a linear term of this quadratic, B is 0, and C is -3. I'm going to use quadratic formula for the remaining zeros. So x equals -b plus or minus the square root of b squared minus 4ac all over 2a. So this becomes a plus, and so 4 times 2 is 8 times 3 is 24. 0 plus that, that's obviously just going to give me 24. So I'm going to simplify the square root of 24, and I'll say, okay, well, that's 6 and 4. 4 breaks down to 2 and 2. 6 breaks down to 3 and 2. So this becomes 2 square root of 3 times 2 is 6. And if you notice, this -0, that's not doing anything anyway. So I can just honestly ignore that. So I get plus or minus, and then 2 times 2 is obviously 4. So the 2 cancels, that reduces this to a 2. So now I get x is equal to plus or minus the square root of 6 over 2. And these are my other two zeros. Now I'll tell you, the rational zero theorem never would have given us these because these are irrational numbers. So the rational zero theorem, the only thing it's going to really help me to do is find those nice zeros. And then from there, I can use quadratic formula to break down the difference. And now we've done it. If you notice, what happened in this section was I didn't give you anything. I didn't tell you anything about where a root was. I didn't tell you anything about whether or not it was a double root. I mean, we found that it was, which is cool, but it wasn't given to you. And then we just sort of found the rest of our roots using stuff that we had done in 3.2. So in this one example, we've got everything we need and more. And I realize I've been misleading you because there's actually going to be one more example we're going to do. Go ahead and pause the video. Try this one on your own. We're going to do this one in its entirety. Okay, first, we use the rational roots theorem. So we've got factors of 2. Well, what are the factors of 2? 1 and 2, no problem. We're dividing it by the factors of 4. Well, what are the factors of 4? We've got 1, 4, and then 2 and 2. Now, here's the thing. I don't need to write the 2 and 2. I can just write 1, 4, and 2 because there's no point in writing it twice. All right, so now let's create our menu. So we start here with 1 over 1. So we get 1 and -1. That's where we're going to start. We've also got 1/4 and -1/4. And we've got 1/2 and -1/2. Here's all of our possible ones just from the 1. Now let's do this second one. So now we've got 2 over 1. That's 2, so I get 2 and -2. 2 over 4, that just reduces to 1/2, which we already have the 1/2s there, so I don't need to write that one. I think you'll find that efficiency is going to be really helpful here, okay? And then we've got 2 over 2, which reduces to 1, so then I've got these two already represented. All right, so we're doing it. So now we've got all of our possible rational zeros. And now we do our synthetic division. And so we've got 4, negative 10, negative 2, and 2. So let's start with, I don't know, let's start with 1. All right, so we'll start with 1. Why not? So 4 times 1 is 4, negative 6, 6, negative 8, negative 8. Again, we wanted 0. So we need a 0 here. We get a negative 6. Well, all right. We tried. That's not going to work. Okay. So we tried that one. Now let's do negative 1. Maybe negative 1 is going to be a winner. Okay, if you really want to kind of like, there's a few little trickety tricks that you can use to kind of help with like your guessing, but I'll tell you they're not intuitive. Yeah, negative 10, so negative 1 doesn't work. If you want to know those, there's so many like little trickety tricks to check and to test. I don't think that it's obvious what those are, and I don't even necessarily know if they're helpful. If you come to an office hour, I can show you some of those. But I don't want to spend a whole lot of time on this in class because, well, then the video would just get super duper long and kind of confusing. Now, let's try negative 1/2. Why not? Okay, so I drag the 4 down. 4 times negative 1/2, that's negative 2. So I get negative 12, 6, 4, negative 2. Oh, yes. Yes, 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 yes. We've got one. We've got one. That's huge. So now, I know that one of the factors is going to be x plus 1/2 because I put negative 1/2 in the box. So now what I'm left with is a quadratic polynomial, and I've got 4x squared minus 12x plus 4. Now, hey, this is a quadratic. So even if I wasn't sure if I could factor this or not, I know that I can use the quadratic formula for this. So I'm done with these for now. I don't need any other fancy pants techniques. I don't need to keep guessing and checking and any of that jazz. I don't need to do that. I can just use quadratic formula at this juncture. So the remaining zeros are hiding in this quadratic. So I've got to find them. Right? Now, just as a note, we already know that one of our horizontal intercepts is going to be at negative 1/2. Right, now we're going to find the other two. So A is equal to 4, B is equal to negative 12, C is equal to 4. So now I'm going to go ahead and use quadratic formula. X equals negative B plus or minus the square root B squared minus 4 times A times C all over 2 times 4. So now I get 12 plus or minus the square root. So what I end up with is this is going to be 144 minus 64. All right. So in terms of the number crunching, I'm going to leave you all to that to do on your own. So I get the square root of 80 over 8. Now, square root of 80, let's simplify this. So I break down square root of 80, let's say 5 and 16. 16 breaks down to 4 and 4, so guess what? I can just go ahead and put a 4 out front. The 5 is left over. You may need to turn your volume up a little bit. My son's asleep in the other room. So I can reduce this 12. Everything has a 4 in common. So x now comes out to the 12 and the 8 reduce to 3 plus or minus the square root of 5 over 2. And now guess what? That's it. That's one of them. That's the other. We've got them all now. We did it. We started with nothing. We came up with these incredibly not obvious horizontal intercepts. Now in Lumen, if I had zeros like this, you could do those in your calculator and type them in decimals. My recommendation to you is to type them in using exact values. And the way that you use the square root is with the sqrt function with parentheses. Okay, I think that'll be really helpful. With 3.5, with these examples, they're big. They just require practice and they require time. I've attached an additional example so that you can kind of see one from scratch. And I chose a big one where there were like an absurd amount of things that you needed to check. Just put your eyeballs on that and continue to work on these problems.